this question, we actually see a couple of things that are really fascinating. Fascinating in the sense that we have objects around, and all these objects, some of them big, some of them small, some of them crooked, and they are found in space. And when you actually determine where these positions of these objects are, and also most likely determine how they move, we see a couple of interesting things that comes out of these particular relationships between all these objects in space. One here is the following. Judging from what you saw on our thumbnail, we saw that G is equal to the big G multiplied by the huge M divided by the R squared. This is really fascinating, and it was derived by some interesting scientists, and we're going to talk about this on our future videos. This huge G here represents the gravitational constant, which is universally known, and the big M represents a specific mass whose mass is pretty much, in this case, or object's mass is the largest. Usually we call it the center mass. Center mass means other objects that are orbiting around it. Let's say, for example, we pick this object right here. There will be some object that is orbiting around it, most likely this, either being the satellite or a particular moon or an asteroid, maybe found the right orbit path. And this R represents the distance from the center of the center mass to where the satellite is located, or any other object is relative to the center of the center mass. So this is really fascinating because this small g does represent the gravitational field, and in space, yes, there is gravity in various locations. Now the big question here is, which part is stronger? What is the value of this particular small g for a specific object in space? And this here is going to be interesting in terms of looking at planetary objects and satellites, where we see a couple of things that are really interesting to be aware of. One is that the gravitational field exists in a space around an object. Let's say, for example, this particular object right here that we pick right here, it has a particular form of gravitational field, and it is around it. And this indicates a couple of things. It indicates that there is a force of gravity acting on other objects around it. Like, for example, we have this object right here, and this object right here shows that it's influenced by this particular gravitational field of this particular object over here. So looking at this, we know that the strength of the gravitational field is directly proportional to the specific mass of the center object, and this central object in this central body is shown right over here. And this is, in this case, the strength of the gravitational field is inversely proportional to the squared of the distance between the center of the body to any other object, in this case the center of this body to another object around it. And so this is really important to take note of, and in here we are going to create a formula that rightly embodies this particular statement. And embodying this statement here comes into play where we combine two things. We combine, one, the law of universal gravitation, and the other one we are going to equate it to, in this case, is the Newton's second law. And the Newton's second law says that there is always, in this case, for a certain object, we have a force that is the net force acting on that object. And so once we're able to determine this, we are going to highlight what the law of the universal gravitation is, which we talked about in our previous video. I encourage you to check it out. And this is equal to huge Fg, which in this case is called the magnitude of the force of gravity. And this here is equal to the product of the universal gravitational constant and that of the center mass, object's mass, and this here is for small m multiplied by small m, which is the satellite's mass, and this here is divided by r squared, which is the distance between the center of this central mass and or to the center of this object's mass. And so this here we have for our law of universal gravitation. Now the other one here is looking at Newton's second law, which is equal to F small g to be equal to the mass of the satellite object multiplied by the gravity, which is the g that is coming from this particular central mass. And so once we're able to accomplish this, we are going to then look at the equivalence, where there is an equal statement between our F big G and that of our F small g, which in this case here is called the magnitude of the force of gravity, and this here represents the Newton's second law, which is the gravity that is acting on the object towards the central mass. And so once we have this accomplished, we can then equate these two equations, which is this and that, together, and we're going to solve for r small g, which in this case, you guys have already guessed it. We have our g big M multiplied by small m, or divided by r squared, is equal to small m multiplied by g. Take note here that we need to divide both sides by r small m, and what we have left is our g to be equal to big G multiplied by big M divided by r squared. So this here is indicating the following. This indicates that as the object of the central body's mass becomes bigger, we have a greater gravitational field from that particular object. And another one here is that if the radius is getting bigger, which is our distance from the center of the object to the center of the central mass, the less is the gravitational field acting on it. So it's actually showing this illustration where if you have this particular small object versus this huge object, then in this case here, our g for this object is way less than this particular object's g. And the reason is because here is that the mass, big M mass here, is smaller than the mass for this. And the other one to keep in mind is that, for example, if you have an object here, that for example, let's relative to this big M, we have one object that is here. Let's make it to be of this particular size, of the same mass as this other object right over here. This object, which is colored in blue, will have a greater gravity field than that of the red. And so this is something really to keep in mind when it comes to that particular relationship. And this is actually due to the distance from the center here to this object, which is the r, to be smaller than that of the r from the center to this particular object here, which is way more larger. But then that results in a gravitational field to be less for red compared to that of blue. I hope you found this really informative. Take note here that the G, which is the big G, we call it to be the gravitational constant or universal gravitation constant. This here is equal to this particular number, which is 6.67 times 10 to the negative 11 newtons meter squared divided by the kilograms squared. And so whenever you're given any question, you should be able to be aware of this particular constant that will be used, and you can determine the gravitational field of any central object in terms of when you're given the mass of it and you're given the distance from its center to any point where a satellite is positioned at relative to that central object. I hope you found this really informative. Please hit a comment down below. Let me hear your thought about this particular analysis of our small g equals to big G multiplied by m divided by r squared, not only in terms of planetary objects, but any other form of satellite that is around it, and how we are able to not only combine our Newton's second law, but also the law of universal gravitation in order for we to arrive at this conclusion that yes, the strength of the gravitational field of a central object is directly proportional to the mass of that central object and inversely proportional to the square of the distance from the center of the object. And hope you found this really informative. By that way, I can talk to you all soon. Stay smart as always and believe in yourselves.